it is genuinely wild to step back and think about how much of our modern world runs on infrastructure that was, well, never actually built for the job.
Yeah, absolutely.
I mean, think about it. You type a really complex prompt into ChatGPT, or you ask an AI to generate a photorealistic image, or maybe you use, like, a coding assistant to just write a whole Python script for you in seconds.
Right.
Beneath that seemingly magic futuristic intelligence,
Yeah.
you were riding on an architecture that was originally designed to make video game explosions look just a little bit prettier.
Yeah, I mean, it really is the ultimate accidental empire, right? We are so conditioned to expect these creation myths of visionary tech founders who just peered into a crystal ball, saw the future of artificial intelligence, and built the perfect machine for it.
Exactly, the whole genius in a garage trope.
Right, but that is simply not what happened here. Not even close.
Well, welcome to the Deep Dive, everyone. Today, our mission is to unpack a really fascinating piece from Tech Reader magazine. We're going to dig into this source material and discover how the most dominant infrastructure in artificial intelligence today was built, like we said, entirely by accident. So, okay, let's unpack this.
The central paradox of the piece we're looking at today is that, well, Nvidia did not see the AI revolution coming at all. They built exactly the right tool for an entirely different reason.
Yeah.
And then they essentially just stood back and watched as the entire global economy reorganized itself around their hardware.
It's crazy. And to really wrap our heads around how bizarre that is, we need to rewind all the way to 1993.
Oh, the Denny's era.
Yes. We are in a booth at a Denny's restaurant in San Jose, California. 3 engineers, Jensen Huang, Chris Malachowski, and Curtis Preen, they sit down to start a company. And their goal was incredibly unglamorous compared to the, trillion-dollar discussions happening today.
Yeah, they just wanted to fix bad 3D graphics on personal computers.
Right.
It's almost comical in retrospect. I mean, they named the company Nvidia, which is rooted in the Latin word for envy. Their highest aspiration at that Denny's booth was literally just to make a PC graphics chip that would make their competitors jealous.
That was the whole business plan.
Basically, yeah. There was zero talk of machine learning or neural networks or global AI dominance.
And it wasn't, some immediate hockey stick growth curve either.
Mm-hmm.
They hit a wall almost instantly with their first product. The NV1 chip in 1995.
Right, and the NV1 is a really crucial detail in the source material because it shatters the illusion that NVIDIA was infallible. They shipped this chip, and it was a massive technical blunder.
Huge blunder.
They made a fundamental bet on how to draw 3D objects, choosing a mathematical method called quadratic surfaces.
Okay, let's break that down for a second because the distinction here really matters. A quadratic surface is basically a perfectly smooth, mathematically defined curve, right?
Exactly.
It sounds great in theory. Like if you want to draw a ball on a screen, you just use an equation for a perfect sphere.
But the reality of computing, especially back then, is that calculating perfect curves for every single object on a screen is incredibly computationally heavy.
It just takes too much power.
Right. So while NVIDIA was betting on these perfect curves, the rest of the industry, particularly Microsoft, which was building the DirectX platform at the time, they realized that approximating shapes was much, much faster.
Yeah.
Microsoft standardized on triangles as the fundamental building block of 3D rendering.
Because a triangle is flat. It's just simple geometry.
Mm-hmm.
If you glue enough tiny flat triangles together, you can sort of fake a smooth curve, right? And the math to process flat surfaces is just blindingly fast.
That's the core of it. NVIDIA built a highly efficient engine for perfect curves in a world that suddenly decided it only cared about fast triangles.
Oops.
Yeah, they bet on the wrong math. So the NV1 became a dead end almost overnight, and it nearly bankrupted the company. I mean, they burned through their cash, they laid off half their staff, and they had to scramble just to survive. They finally emerged in 1997 with the Rive A128, which was a chip that completely abandoned quadratic surfaces, embraced the triangle standard, and basically saved the company.
Okay, so they survived the 90s, which brings us to 1999 and the release of the GeForce 256. This is the moment NVIDIA invents a totally new marketing category, right? The GPU,
Yep.
or graphics processing unit.
Yes.
They had to convince the world that this wasn't just like a plug-in accessory, but a fundamentally different brain from the CPU, the central processing unit that ran the rest of your computer.
And understanding the difference between those two brains is the absolute key to understanding the AI boom 20 years later.
So I was thinking about it like this. Imagine your computer's CPU is a master chef in a Michelin star restaurant.
Okay, I like this.
This master chef is incredibly smart and endlessly capable. If you need a complex 5-course tasting menu prepared, the master chef can do it perfectly, right? Adjusting temperatures, timing the sauces, plating the dish.
Right, very versatile.
Exactly. But the chef works sequentially. They do one highly complex task at a time. Now, imagine a GPU. A GPU is not a master chef. A GPU is an army of 10,000 line cooks.
Okay.
These line cooks do not know how to make a beef Wellington. All they know how to do is chop carrots. But if you give them 1,000,000 carrots, they can chop all of them at the exact same time.
That is a brilliant way to visualize the architecture, actually.
Yeah.
The master chef represents sequential processing. The army of line cooks is parallel processing.
Right.
Because beneath all the flashy marketing about gaming and realistic lighting effects, a GPU is really just doing the same simple mathematical operation, literally multiplying two numbers together millions of times simultaneously.
To chop the carrots.
Exactly. To render a 3D video game frame, you need to calculate the light hitting thousands of tiny flat triangles all at once. The GPU was built specifically for that mass synchronized calculation.
But having an army of line cooks is only useful if you're running a massive banquet, or in this case, playing Quaker Doom, right? No one outside the video game industry was thinking about how to use an army of line cooks for anything else.
Which is exactly where the narrative shifts. Between 2004 and 2007, Nvidia makes a bet that flies completely under the radar. It centers around a computer science PhD student at Stanford named Ian Buck.
Right, and Buck was doing something highly unusual with a couple of consumer Nvidia graphics cards, wasn't he?
He was. He was looking at these gaming cards and recognizing the raw computational power they held. But the problem was, all that parallel power was locked behind graphics programming.
Right.
If you were a scientist wanting to simulate fluid dynamics or maybe track folding proteins, you couldn't just write normal code and send it to the GPU. You literally had to trick the graphics card into doing your math.
The source material gets into this, and it honestly sounds agonizing. You had to disguise your science as a video game.
It was incredibly tedious. You couldn't just input numbers. You had to map your physics data onto graphics concepts like vertices, which are the corners of 3D triangles, and shaders, which are the programs that calculate the color of a pixel.
Right.
So scientists were taking their complex physics variables and literally hiding them inside the red, green, and blue color channels of a fake digital texture, just to force the GPU to process the math.
That is absurd. It's like, I don't know, forcing a poet to write an entire novel using only an Excel spreadsheet.
Yeah, it was a massive headache. So Buck builds a programming language called Brook to bypass that bizarre translation process. Nvidia notices his work, they hire him in 2004, and they pair him with an engineer named John Nichols.
And their mandate was to build a platform that would let anyone use GPUs for general-purpose parallel computation.
Right, which they called CUDA Compute Unified Device Architecture.
Okay, wait, what's fascinating here is what CUDA actually represented and why the lack of reaction at the time is so profound. CUDA stripped away the graphics metaphors completely.
Yes.
The fake textures and color channels were gone. A physicist or a climate scientist could suddenly access those 10,000 line cooks by writing in standard C, which is a language they already knew.
Exactly.
But wait, I have to jump in here. If I'm a researcher spending half my year hiding math inside blue pixels, and someone gives me a magic bridge to just write standard code, I'm throwing a parade, right?
You would think so.
But the piece notes that when CUDA was released in 2006, the mainstream press completely ignored it. Investors actively hated it because developing it was eating into Nvidia's margins. Why were people asleep at the wheel? Were the scientists just too stubborn to learn software from a gaming company?
No, it wasn't stubbornness at all. It was that CUDA in 2006 was just the raw bridge. You could cross it, but there was nothing on the other side yet.
Oh, I see.
Getting parallel compute to work efficiently on complex problems still required an immense amount of foundational effort from the users. And that's the hidden flywheel here. The real value wasn't just releasing the CAD platform. It was what Nvidia quietly did over the next 6 years.
They started building the specific tools for the scientists.
Hand-tuning libraries, exactly. They built CUBLAs for linear algebra, which is the foundational math for tons of scientific modeling. They built CUF-FT for signal processing, which is used in everything from radio astronomy to medical imaging. Imagine trying to use your army of line cooks, but having to teach them individually how to chop the carrot every single time.
That would take forever.
Right. So Nvidia wrote the fundamental hyper-optimized cookbooks for every major scientific discipline. It took years, and they weren't getting a lot of credit for it. They were quietly laying a massive software trap 6 years before anyone even knew there was a war to fight.
It's just a staggering long-term play. They built this frictionless engine of mass computation and then just sat back and waited for a problem big enough to require it.
And that problem finally arrived in the form of deep learning.
Right, so the collision happens between 2009 and 2012.
Yes.
Enter Fei Lai. She's a computer vision researcher at Stanford, and in 2009 she releases something called ImageNet. It's a data set of 14 million labeled photographs.
Massive amount of data.
Yeah, and her foundational belief was that artificial intelligence wasn't suffering from bad algorithms. It was suffering from a lack of world experience. The AI just needed to see more data.
She organized an annual computer vision competition around ImageNet. For the first few years, researchers used traditional, hand-engineered algorithms to identify objects in the photos.
And how did that go?
Well, the progress was real, but it was incredibly slow and incremental. Then, in 2012, the paradigm breaks entirely at the University of Toronto.
This is Alex Krzyzewski.
Yes. Krzyzewski was experimenting with deep convolutional neural networks. Now, the theory of neural networks, these algorithms, loosely inspired by the structure of biological brains, with multiple layers of nodes passing information that had been around for decades.
Right, it wasn't a new idea.
Not at all, but the academic consensus was that they were a dead end. Training them required an impossible amount of computation.
Let's bring back our master chef for a second. If you want a neural network to recognize a picture of a cat, you have to adjust millions of tiny mathematical weights simultaneously based on the pixels in the image.
Right.
It's like trying to perfect a soup by adjusting 10,000 different spices. A CPU, our master chef, has to taste the soup, adjust one spice, taste it again, adjust the next spice. It would take months or years to process those 14 million images.
But Krzyzewski realizes that training a neural network is fundamentally a massive parallel math problem. It is matrix multiplication.
It's the line cooks.
It's the line cooks.
Yep.
If you give the 10,000 line cooks 10,000 bowls of soup, they can adjust one spice in each bowl simultaneously, compare the results instantly, and find the perfect recipe in seconds.
And my absolute favorite detail from the source material is where this breakthrough actually physically happens. The deep learning era, the foundation of the modern AI boom, literally fires its starting gun in a guy's bedroom.
It's wild.
Krzyzewski buys 2 consumer graphics cards, GeForce GTX 580s, right off the shelf at a standard computer store. He installs them in his bedroom at his parents' house, and he trains his neural network, AlexNet, on the massive ImageNet dataset over 5 or 6 days.
And the results of that bedroom experiment caused a total rupture in computer science. When they submitted AlexNet to the ImageNet competition, it hit a top 5 error rate of 15.3%.
And to put that in perspective for you, the second place entry, using traditional hand-coded methods, was at 26.2%.
A gap of over 10 percentage points in a field that usually fought tooth and nail for fractions of a single percent. We really have to make sure the gravity of this is clear. This was not a slightly better iteration.
Right.
It was an overnight rewriting of what was possible in software. Suddenly, every computer scientist in the world knew that deep learning worked. The algorithms weren't the problem. The hardware was. You just needed enough parallel compute power.
Wow. So with AlexNet proving beyond a shadow of a doubt that parallel computing was the key to intelligence, how did Nvidia capitalize on this while tech giants like Intel and AMD were caught flat-footed? Because they both make incredible chips.
They do, but Nvidia recognized the inversion faster than anyone else. They saw that the most important application of their hardware was no longer physics simulations or video games, it was intelligence.
So they pivoted.
They pivoted hard. They took their Tesla product line, which, by the way, is completely unrelated to the car company, for the record.
Good to clarify.
Yeah, and they repositioned it strictly for data centers.
Which leads to 2017 and the release of the V100. This is a massive turning point because it's the first chip Nvidia builds explicitly for AI training. And they introduced something called tensor cores.
Right, and this is a vital technical shift. Before tensor cores, a GPU core would take 2 numbers, multiply them, add a third, and output a result.
Okay.
A tensor core doesn't just look at 2 numbers. It grabs an entire block of numbers, a matrix, and processes the entire block in one single hardware clock cycle.
Oh, wow.
Yeah.
It's like upgrading the line cooks from regular knives to, like, industrial slap chops. Instead of slicing the carrot piece by piece, they obliterate the whole carrot in one punch.
Exactly. And it does it at slightly lower precision, which matters immensely for physics simulations, but turns out to be perfectly fine for training neural networks.
Oh, interesting.
The V100 wasn't a gaming chip with compute bolted onto it. It was an AI brain that just happened to be able to run graphics. And the costs reflected that shift. A single DGX-1 server packed with V100s was around $150,000.
$150,000.
Yeah, and research labs and hyperscalers couldn't buy them fast enough.
But again, Intel and AMD are massive companies with endless resources. They tried to build their own parallel computing ecosystems, right? AMD had ROCm, Intel had one API. Why did they fail to dent Nvidia's dominance?
Well, they misunderstood the shape of the moat. They thought it was a hardware race. But the actual moat was cultural. It goes back to the software trap we discussed earlier. By 2017, an entire generation of developers had been trained to think natively in CUDA.
Let's flesh that out, because cultural moat sounds a bit abstract.
Sure.
If I'm an AI researcher, my career relies on publishing papers quickly. When I encounter a bug in my code, I go to websites like Stack Overflow to find the solution. And every single solution on those forums was written for CUDA.
Exactly. Not only that, but the major AI frameworks, the actual scaffolding researchers use to build models, like Google's TensorFlow or Meta's PyTorch, they assumed CUDA was the baseline reality of the universe.
Right.
If a researcher wanted to use a slightly cheaper AMD chip, they would find that their code simply wouldn't run without spending 6 months rewriting it from scratch.
Who has time for that?
No one. Replacing CUDA meant throwing away a decade of community knowledge, debugging tools, and all those hand-tuned libraries. The switching costs weren't just technical, they were career-threatening.
Here's where it gets really interesting. By the time we hit the 2020s, that cultural moat has essentially hardened into an impenetrable fortress. You look at the H100 chip, announced in 2022.
It's a monster.
The specs are absurd. 80 billion transistors. It operates at performance levels measured in thousands of trillion operations per second. It costs between $30,000 and $40,000 for a single unit. And the demand is so ferocious that waitlists stretch for months.
Yeah, by 2026, estimates project Nvidia holding upwards of 90% market share for global AI model training. The H100 literally became the primary unit of currency in the tech world. Startups couldn't get funding unless they could prove they had an allocation of H100s secured.
Which brings us to the climax of this hardware story. November 2022, and the launch of ChatGPT. OpenAI gets 1 million users in 5 days. The public is entirely focused on the software, praising OpenAI as the wizards of the new age.
But the infrastructure story is entirely NVIDIA. Every massive training run for GPT-3, GPT-4, it all happened on NVIDIA hardware.
Right.
Every time you ask ChatGPT a question today, the inference request, the actual generation of the answer is processed on a CUDA application. They became the inescapable toll booth for the AI economy.
And NVIDIA skyrockets to a $3 trillion valuation. Jensen Huang is suddenly a global celebrity, walking around in his signature black leather jacket. But, that level of dominance invites a totally different kind of pressure. Geopolitics officially enters the chat.
Right. And we have to look at this objectively based purely on the reporting in the source material. The United States government became deeply concerned about advanced AI chips finding their way into Chinese military applications.
Okay.
So to prevent that, the U.S. implemented strict export controls, legally restricting the sale of the most advanced chips, the A100 and the H100, to China.
And NVIDIA even tried to create downgraded versions, right?
Yeah.
The A800 and H800, to comply with the new rules while keeping the market open, but eventually those were restricted as well.
Yes. And if we connect this to the bigger picture, the downstream effect is a profound irony. The export controls were specifically designed to impede Chinese AI development. But by completely severing them from the CUDA ecosystem, the government inadvertently created the strongest incentive in history for Chinese labs to build a genuine non-CUDA alternative.
Oh, wow.
Because they literally can't buy NVIDIA hardware, they are forced to endure the pain of figuring out how to train competitive models on domestic chips.
It's the ultimate unintended consequence. They essentially force the creation of a parallel ecosystem. But it's not just international pressure, is it? Inside the U.S., NVIDIA's biggest customers are also trying desperately to find the exit door.
Oh, absolutely. The hyperscaler tension. Companies like Google, Amazon, and Microsoft are NVIDIA's most important partners. They buy chips by the hundreds of thousands.
Yeah.
But they are also terrified of being so completely reliant on a single supplier who controls their profit margins. So they're all designing their own custom silicon. Google has their TPUs, Amazon has Trainium, Microsoft has Maya.
They want to build their own toll booths. But they can't quite escape, can they? I keep thinking of it like a hotel chain.
Yeah.
Well, the hotel might want to manufacture its own brand of mattresses to save money. But if the corporate guests threaten to check out because they demand a specific luxury brand mattress,
Hmm.
the hotel is going to swallow its pride and buy the luxury mattress.
That analogy perfectly captures the central tension defining the market today. Google, Amazon, and Microsoft can carve out niche workloads for their own chips, maybe running simple inference tasks at scale. But when it comes to the massive training runs that actually push the frontier of AI, Nvidia remains the default.
I just have to buy them.
They have to. Their enterprise cloud clients have built entire company workflows on CUDA, and they absolutely refuse to abandon them. The hyperscalers are essentially trapped by their own customers' preferences.
Wow. So as we zoom out to wrap this up, the scope of this journey is just incredible. We're looking at Jensen Huang, who has steered this single company for 33 straight years. From sketching ideas in a Denny's booth, through the catastrophic near bankruptcy of the NV1 chip, surviving the GPU wars.
Making the massive software gamble on CDA when no one understood it.
Exactly. Colliding with the deep learning revolution and arriving at a $3 trillion valuation. Every time you engage with the modern AI economy, you are fundamentally relying on an architecture born from a desire to draw video game triangles a little bit faster. So what does this all mean?
Well, I think the source material leaves us with a very compelling question about vulnerability. Let's go all the way back to the beginning. Nvidia almost died in 1995 because they bet on quadratic surfaces, the wrong math, while the world moved to triangles.
Right, the perfect curves versus the fast, flat approximations.
Today, their entire deeply entrenched empire is built on the massive parallel matrix multiplication required by current deep neural networks. They are the undeniable, unchallenged kings of that specific type of math.
Okay, I see where you're going with this.
What happens to this seemingly invincible fortress if the next massive leap in artificial intelligence requires an entirely different kind of math?
Wow. If the paradigm shifts away from matrix multiplication, do the 10,000 line cooks suddenly become obsolete?
Exactly. Are they back to betting on the modern equivalent of quadratic surfaces?
That is a truly fascinating thought. We will leave you with that to ponder. Thank you so much for joining us on this deep dive. Keep questioning the hidden infrastructure behind the tools you use every day, and we'll see you next time.